And anyway, in general, we don't know what an atom exactly is. But he said there's something we know, and that is that atoms are made of at least 99.999999% space. And I was mind blown by that answer. I was like, oh my God, it's mostly space. And because it doesn't feel that way, I mean, it feels pretty solid. When you hit your head against a wall, it hurts. All this stuff. So it's like, that's mostly space. And so I started to think about it. And that's when I realized that the vacuum structure must have something to do with it. If I asked you today, let's assume that there's something that connects all things, that makes sure that all things communicate with each other so that we can have this level of complexity today. What would be that thing? How would you, if I asked you to point out what connects all things, the only thing you could come up with, if you thought about it for a while, could take you a few years or a few minutes, would be the vacuum, right? There's vacuum at all levels. Vacuum is everywhere. The space is everywhere. And so, for me to realize that there's 99.999% vacuum everywhere, and especially in atoms, started to realize that the vacuum might have something to do with this. And I realized that maybe atoms are just like little divisions of the vacuum. Maybe the vacuum is what's really there, and the divisions of the vacuum appears to us as reality. It's a difficult thing when you work in the context of mainstream physics, science, and so on. You can't really alter words too much, because if you do, then they don't know what you're talking about. So like the tendency, for instance, in the public, is to think of the vacuum as something that's empty, and really actually, even in the physics world, even like top physicists that I talked to about that, and you talk about the vacuum, and they're visualizing either a chamber that's being evacuated, right, on Earth, or, a place with nothing in, The thing is that there's no such thing. There's really not an absolute vacuum anywhere. Even intergalactic space, which is the largest vacuum we know, millions and millions of times more vacuum than anything we can produce in a chamber on Earth. In that case, the molecules are only centimeters apart. See, so that's how dense it is. But when you actually look at quantum theory, the vacuum means something even more dense, more incredible. So I was at that chemistry class, and that teacher told us that the atom was made out of 99.99% space, and that's when I started to examine the concept of the vacuum, and I started to think, and during my seminar I'll show, scaling law that shows that the vacuum actually divides itself, but I started to think maybe what we call reality is just divisions of the vacuum. Right? Actually, the only thing there is the vacuum, and when it divides, then we see it. Right? Like when there's a division, when there's a boundary, when there is an event horizon, right? Then we see the result, and we see the result because there's energy in the vacuum, and when a boundary is generated, there's kind of a dislocation of the vacuum, and when that happens, electromagnetic fields are radiated. And so that becomes apparent to us, because now there's radiation, right? And we call it an atom, we call it a sun, we call it a galaxy, whatever. So I started to think in those terms. Scaling space-time, scaling structures of vacuum division. And I started to study, and again, in that big book, Gravitation, I found something very significant. I had figured this out before, but it's a good quote from that book. Although that book is not a quantum physics book, it mentions this in the middle of it. Present-day quantum field theory gets rid by a renormalization process of an energy density in the vacuum that would formerly be infinite if not removed by renormalization. Okay. That's quite the statement, isn't it? Now, what is renormalization? Renormalization is what they tried to do to me at school. Not quite. They didn't succeed, as you can tell. Renormalization is a typical trick that's used in physics to get rid of infinities. Okay, in physics, there's two types of infinities. There's one type of infinity that's a quantity that's infinitely small. So like 0.00000, 1 is so small that you can discard it, right? You can make like it's not there. It's okay, Those are infinities, they don't mind. Okay? Then there's what's called, very technically, actually, you find that in technical books, nasty infinities. Okay? Nasty infinities are quantities that are infinitely big, right? So that is not an infinity that you can just say, well, make like it's not there, right? Because it's an infinite amount of something. And so you got to deal with it. And in general, if a theory gives a result that says nasty infinity, that says this is an infinite amount of something, the theory is either discarded or renormalized. Okay? Renormalization means that they use some fundamental physical constant, they apply it, and they cut the number. They say it's a finite number. Right? So, what they did is when quantum theory started to analyze the structure of the vacuum at the quantum level, that means at the atomic level, or subatomic particles, they realized that in order for the particles to do what they were doing, to have the energy they have, the vacuum, the equation gives infinite amount of energy. There's got to be infinite amount of vacuum energy for atoms to do what they do. And that was not acceptable. So what happened is that they used the Planck's length. They got rid of the infinity by using the Planck's distance, which is 1.616 multiplied by 10 minus 33. Just happens to be very close to a phi ratio, by the way. That is a mathematical constant that's given for the smallest thing the universe does. Okay, it's billions of times smaller than an atom, even smaller than the Higgs boson. They're looking for it actually with that accelerator. They're trying to get mini black holes, mini white holes to appear. But the Planck's distance is what we assume is the end. The universe goes to that, and then it goes, that's it, that's small enough, I'm not doing anything small. That's it. Okay, now, it might be a fundamental boundary, but that boundary is most likely just that, a boundary. And that's the boundary that we can experience in terms of our capacity to solve the physics at hand. So they used that, and what they did is they used that little concept of a small little Planck's distance, and they took a centimeter cube of space, a centimeter cube of vacuum, and they said, how many of these little Planck's distance would we have to put in that centimeter cube of space to fill it up? And that'll give us a finite number for the energy of the vacuum, for how much energy there is in the vacuum, and we won't have this nasty infinity at the end of our quantum view. Wow. That's one way to go about it. And so they took little Planck's distance and they stacked them up. Right? Now, at the end of the equation, when they calculated how many of these little Planck's distance they had to put in there and what's the density of a centimeter cube of vacuum, the density was still, and it's still to this day, 10 to the 94 grams per centimeter cube. 10 to the 94, that's 10 with 93 zeros on the end, right? Okay? Grams of, energy, per centimeter cube of space. Now, that is a very, very, very large number. That is an extremely large number, and if you were to try, if I was to try to give you an example, an idea of what that is, if I took all the stars we see in the universe with the Hubble,